So, did you have a good break? Okay. As NJ have said in the previous lecture, I think it's really important to set up basic questions to depart, to launch your project, I think. And I think it already some kind of design ideas are already embedded inside the question actually. So I think you all need to construct sort of personal opinion or personal idea about some sort of philosophical idea even about what data you are gonna look for, you're gonna look into, or even how you define a problem or a situation or a question. I think it's a very important first step. Okay, then shall we move to the second part of this session? Okay, thank you, NJ.
Thank you for summarizing what we learned. Thank you. Yeah, so we have a main dish here. Yeah, let's jump to this link. So we mainly dealing with network system for our urban analysis, right? So today I am going to talk a little bit about, the network theory or technique behind the scene. So I think you guys already saw this kind of, diagram or I don't know, infographics, whatever. So we have a lot of data, and then with the filter, data can convert information, right? And the information has some connectivity, and then they become knowledge, right? And then inside of the knowledge, it has a particular, like a location in that knowledge graph. It becomes insight. And then if you connect among insights, then it becomes wisdom. I don't know whether you agree or not. I think I can just try to read this diagram throughout my lens. So at the end of this slide, you are able to answer this kind of question. The first question is how to capture and process spatial data for your design. Correct. This is the first question. The second question is how to create the relationship between data or place in a space. And then the last, most important, sorry, the most important question is to how to discretize a space into small portion or part that is computable, demand. So first one is graph. The graph is a really, really important and old thing in history. So I think the math or computer science, they have their own sort of domain to study graph. Yeah, graph is some of a mathematical object, as I mentioned here. It consists of points and edge. That's it. This is basically like how we abstract something. So the graph is not just describe the image that you can see, or not just describe subways like a system, or I don't know, maybe highway or freeway. It's not only we can describe the tangible stuff, but also we can do make some abstract hierarchy in your mental structure. I think this is really important. Yeah. And then the pixel and voxel. So let's say I can replace the pixel with the matrix. Yeah, the matrix is a sort of a very
Okay, MJ,
Yep, go ahead.
I just had a quick question about the graphs. You said like you can create a hierarchical structure. Can you explain that a bit? Like, what do you mean by that?
Yeah, I mean, these structures looks like it has no sort of hierarchy, right? It has only connection. So I think that you try to think about like the tree structure, right? So, so we can see it on the top. We can consider this is a root, right? And it has a branch and branch. Also, we can see this configuration as a graph. Also, we can see this graph as a tree. Yeah, it depends on how you want to cook the data structure. Okay, correct. Then the pixel voxel is basically, you know, describing a space. Yeah, pixel is usually for your screen. Yeah, my smartphone here, my screen is two-dimensional array of pixel. So individual pixel like shift their color or strength. Yeah, so that we are able to see the entire picture. Yeah, which is out of a small individual pixel, right? And if you extract or like extrude along the z-axis, just like think about Minecraft. Yeah, I've never played Minecraft, but my nephew really loved it. So, but I saw it in Minecraft several times. But it's like entire like a voxelized world. Yeah, this is I think it's a good example. How we discretize in a space in a voxelized small like a level like block. You know, this is all about like a voxel. It's nothing special. But the most important thing is that how we make a connection. Yeah, we'll talk about it later. Okay. So partition is let's say a little bit different lens of you know, this kind of like a, let's say, discretized space. So let me click the linear regression because these days everyone talks about machine learning. So I'm just pick the example like this. So linear regression is simply we wanted to try a fitting curve based on the data, which is perfectly fit within the given data, right? So using the, there's a lot of cost functions such as I-square, yeah, that we already described in the previous session, yeah. So, but we also see this linear regression a little bit different perspective with our like a partitioning perspective, let's say. So I draw a line, correct, and then we can separate them into two parts. This is also one concept, how we separate them, right? Because in order to partition something, it's all about like a separate, making some group. KMM is you know, one of the sort of old but very robust algorithm to create some partition like this. So think about, you have a data like this. Now, whatever data, you can just visualize it. Your urban data, or your construction data, or I don't know, whatever data. And then we can, because in order to deal with the sort of the data, we have a dimension, right? So in the computer science, let's say data science, we call it observation along the law, and column is a dimension. Yeah. So usually vector has a 3 dimension, right? So we can replace this as x, y, and z, right? However, in computer science, particularly for the machine learning, we call vector. The vector has an n-dimensional space, right? So in this case, we only reduce multiple dimension into 2 dimensions, for example, like along the x and y. And then we can project all the data in that space. So using the KNN, they try to create some partition, right? They try to separate the data characteristic based on their characteristic. This is also one way of how to, you know, decompose the space into small part. Correct, right? Let me take the other example, support vector machine, which is also machine learning algorithm. Where are you? Yeah, this is the example here. This is also, how they draw the line between group. Yeah, the support vector machine has their own the mathematical equation and KNN as well. We have a question. Okay, yeah, thank you. Yeah. And also we have a random forest. Yeah. So random forest is I really like the name of algorithm, random forest, because we have a tree structure, decision tree, right? One is from the root, we have a decision. Yeah. We basically, this is, let's say, abstract sort of partitioning, right? Yeah, out of our data. So if you have a large of decision tree, it becomes forest. So that's why we call it random forest, by the way. Anyhow, this is also, in case we have data, they're trying to partition them, like separate them, and group them based on their characteristics. This is also the other way of looking at how we, decompose space into small parts. Okay. I'm just trying to make some sort of brainstorming with you guys to open, don't stop into one area. And this is one of my exercise. There's a really good example in coding train. I like the guy who developed the processing. He's a very funny guy, anyhow. So this is actual problem. So basically, think about it. The line is not necessarily just simple curve or linear or non-linear curve. Sometimes we can partition them based on the strength of the color, for example. It's really hard to say, maybe this color strength talks about the probability. Yeah. So if you around here, maybe let's say you are basically belongs to that group. However, if your data point is around here, the probability, maybe the black is 0.7 or the red is 0.2, things like that. Doesn't necessarily, I mean, in order to partition a space, we can not only use the line, but also we can use some of probability, okay? This is the idea behind this. You don't need to understand everything, just understand the hierarchy and mental structure thought process, okay? And then this is the Tensorflow Playground, which is very interesting things. Yeah, the Tensorflow, which is one of the famous machine learning library these days. So as you can see, they're trying to draw the line, like a group, yeah. One of my understanding of deep learning is all the neuron has their own sort of linear regression, and then they actually try to draw the line, and then the space is distorted. Yeah, this is just one of my understanding of looking at the CNN, convolutional neural network. So as you can see, as the iterations keep going, we are trying to separate in a space, just like this. Because they are very clear data, yeah, not too bad. But what about this? Ooh, they try to optimize, yeah. I feel like this looks like overfitting, but that's okay because we are trying to understand the partition concept, right? So this is also one way to understand how we, decompose the space. That's why I guess the machine learning heavily rely on the linear algebra, by the way. And then we can narrow down a little bit. So Delanoy algorithm. I think some of you guys are already familiar with because the Grasshopper has the command for the Delanoy here. So here, this is the algorithm. This is the given data point. Yeah, I mean previously we talked about partitioning based on the density of the data, right? But in this case, also it talks about density of data, but more importantly, it has its own geometric algorithm, right? How we decompose, how we tessellate the space, correct? So it's like a midpoint and circle. This is how the Delanoy algorithm works behind the scene. And then you're also easily able to, let's say, Voronoi algorithm here. This is all about the partitioning space, right? If you are interested in, there's a link. Just go to the wiki and then just read them. Nothing special. And discrete space. I think this is also very, let's say, important and very well-known, let's say, area. So discrete space is in topology, topology is more about like a connectivity, let's say. Yeah. So many people make an example, donut and the mug cup has the same topology when they're trying to make an example. Yeah. So topology is all about like connectivity. So the discrete space is so one of the way of how we convert a space in a basically abstract a space. Yeah, and then distill and then revealing the topology. So think about it. Graph itself is just topology. It's nothing special. This is topology. But however, that one is we basically entirely capture entire space. Yeah, this is the only difference anyhow. So this is the other space partitioning space. Space partitioning in computer graphics. Yeah, not computer graphics like rendering things. It's more about like dealing with geometry. The computer graphics is also one of the branches from the computer science. So, for example, like how we group them and make some graph. Think about the game, right? So, as I said, I know only one game, StarCraft, right? StarCraft has its own world. I click. So, for example, like a Marine or like tank or race, which is a unit in the StarCraft world. So, in this case, it's really hard to pick an object out of my mouse here. So in this case, we use this kind of partitioning here. So also, I will describe it more deeper later. Also, the partitioning things is also really important for the fabrication to reduce your material, right? So the other day, I asked my friends are asking me like, NJ, we have this kind of sheet. Is it possible to maximize put our sheet in a small space, or like because once you use the laser cutter or water jet, the rest of the material is gonna be go to the trash can, right? So the packing is also really important. Yeah. So I think I'm just trying to mention it. And here we have a quadtree, octree. Quadtree.
Hey MJ.
Yep.
I just had a quick question. Can you explain a little bit, like, is discrete space kind of like if you have like a grid or something?
Grid?
And you have, yeah, like what exactly is discrete space? I don't think I understand.
Okay, so I mean, my understanding of discrete space is basically you can decompose space into small parts. Yeah. So for example, like in the real world, we have this many space this much space, for example. Yeah. But there is an infinite coordinate system inside of this space because we can infinitely zoom in, right?
Mm-hmm.
But in some point, we need to, give us some limitation. Yeah, let's say 1 millimeter is our limit. So now, actually, you're trying to discretize the space. Now, 1 millimeter is become a small unit to capture, to represent individual space, right?
Okay.
Yeah, I mean, this is the basic concept, and then you can actually expand this concept towards up to your imagination. I mean, I try to, insight your brain to imagine. Yeah. So
it's just like unitized in like I guess like a grid or something like that on space.
Yeah, you can also think like that. Yeah. But one important thing is that discretization. I mean, this is you can search it. There's a lot of article in terms of discretization. Particularly, let's say, let me make an example like fabrication, right? So you can draw a double dip like curve like this in Rhino. Yeah. There's no machine, duplicate like create this double dip surface in real world. There's no way, right? So we need to tessellate, or we can make some some triangle surface. Even if you use the 3D printing has its own resolution. Yeah. So also, this is kind of the limitation from the digital world to real world. Also, the real world information is infinite information. We need to discretize. So, for example, like float number, integer number. This is all about discretization, right? Because
Right.
there's no data type that contain infinite number. Yeah.
Mm-hmm.
Thank you for raising the question. Yeah. So we are faced the quad tree. The quad tree is a special algorithm to pick a entity in a space. So for example, there's a bunch of points here, right? If I click this point, I'm only search this rectangle. Yeah. Otherwise, I need to check all the points with my mouse, whether I'm picking one up. So I need to find the distance check, and then I need to compute which one is the closest point toward your click, the place you click. However, we can discretize. You can basically partition in a small portion. So if I click it, there's only 2 points here. So I'm just comparing only 2 points. Yeah, this is the really important technique for the computer graphics. If you are familiar with the WebGL and OpenGL to build your own CAD system, so you need to understand this kind of system. Oak tree is nothing special, but it has a 3 dimensions, just like a box cell. Yeah, it's like this. Okay, let's move a little bit. We have a little limited time, so I can jump a little bit quicker. Here's a graph, right? But unfortunately, I already made in my video of the graph and pixel boxel in Korean version, but I have no version of English. So for the Korean people, you guys can visit this link and then you can see my video anyhow. So this is the example how we use the graph in different domains. Okay, the social network, right? So this is very familiar with you guys, right? Facebook, right? So if you have a friends and then you literally visualize your friends over friends, right? And then friends over friends over friends, things like that. So because it's more about the connectivity, so let's say ontology of the social network. So we can use the graph to describe the connectivity. And obviously we have a street, yeah, just like that. And highway, freeways, subway, right? It's Manhattan, yeah, and even skyway, yeah. So we can encapsulate, we can abstract this kind of path by graph, right? Because we know the place and connectivity. This is the essence of the graph. And also we have a fold structure, yeah. So you mentioned the tree, right? So maybe we can consider this is the top, right? And they have branch, branch, branch. Every software heavily rely on this kind of let's say, tree structure. If you open the Rhino Common API, which is the Rhino SDK, we can use the Python or C#. They also arrange their own API in that fashion. Yeah. So now we know like a tree or graph structure is really good at some not discretize something, but in an abstract way, you can organize group them or separate them, right? This is also a very important way to dealing with the data. Yeah. Program execution. Yesterday, the day before yesterday, we had a workshop, right? Python workshop. So the Python or the C# or other code, they actually execute line by line from top to down. This is also the flow. However, if there's make the if statement, or let's say if you are familiar with the class has method or function, that one is actually jump to other one. And then inside of the function, it has some if or conditional statement, and then that they call the other function. So basically, this is a flow of data, flow of action sequences. So we can also describe or abstract this flow as a graph. And zoning, recently, zoning is also, we can represent as a graph, yeah? recently I faced a lot of, let's say, people here. He's one of my friends. Yeah. The Autodesk, I mean, GAN is one of the popular network every designer fascinated in. Anyhow, using the GAN, they are using graph sort of approach. So basically abstract the space, the graph. Do you know why they, just think about it, why they, try to abstract the space into the graph? This is very obvious to me because the graph is really easy to convert to data. Yeah, but this is image. So we can also use image because the deep learning these days is fairly good to extract the information out of the image. But however, the graph is more explicit data. I will describe the CSV or let's say Json or GeoJSON later. So Json or GeoJSON is all about the graph. Yeah. So I think now we know how we convert real world problem or real world data, how we abstract that one into the graph. I think this is also really important concept. Okay. Just in my opinion, I have a lot of friends like New York and London and Europe, computation designer friends. So whenever I visit the city, I meet them, and sometimes the other day I went to a construction firm. So they actually built the TP library. Anyhow, so not most computation design are familiar with this kind of algorithm that help us to occupy the space, like a graph or pixel or data structure. I think this is very important things. Yeah, if you want to really become strong computation design, not just understand the API, but more about understanding data structure, because algorithm is all about to tweak the data structure, to be honest. Okay, I have a question here. Yeah, absolutely. Yeah, I totally agree. So he said, we prefer to convert data into graph because it is easy to manipulate and take less computation time and memory. Correct. Yeah. Thank you for summarizing. Great. And also we have the other example, associative geometry, which is Katia, right? Katia is a really strong parametric system. And they actually heavily rely on this kind of relationship behind the scene. So I'm also interested in the building energy. So when I was in the school, I took the CFD, computational fluid dynamics simulation. Also, I learned one software. They also rely on the let's say, associative geometry. I mean, the graph is not just for the create the network system. As long as once you're familiar with the way you looking at the world is absolutely upside down. Yeah, because this is like give us a really good foundation or mental structure to decompose the problem. Okay, and also we have an interface, right? Grasshopper, yeah, our friend here. Yeah? Grasshopper is graph, right? It makes sense. So this is the entry point. We compute something, but that one is the linear sort of, not iterative, just one way, linear computation things. Yeah, but it has pros and cons. But yeah, this is the example. What else do we have here? The neural network. Yeah, this is TensorFlow, the TensorBoard. The TensorFlow is let's say I'm not going to talk about TensorFlow deeply, but they declare inside the system, they declare the constant and the function and cost function and whatever optimizer as a node here. So TensorFlow is basically create the graph and then you execute the graph to train your network. Yeah, this is also one of the examples how we use the graph here. And also structure, as I mentioned, the structure, yeah. But think about it, yeah. This looks very complicated, right? However, in order to compute, I mean, I don't know. In my opinion, in my experience, if you ask this one to the construction engineer, they try to abstract them. Yeah, Otherwise, there's no way to compute. So for example, like, where am I? Okay, here. Yeah. So even the complex building, we can decompose like just like this. Yeah, node and edge and node and edge. Yeah. And then even the node and node, we have an edge, and then we can tessellate, we can discretize this length into small part based on your resolution. Yeah, this is also graph and discretization. So think about the one mesh here. This is sort of a resolution. Yeah, you can give a more resolution, higher resolution, it makes sense, but the computation expense is going to be skyrocket, right? It makes sense. So this is an example of the structure. And then polygon mesh. You know what? Polygon is actually, this is the graph. Yeah, this is graph. So think about it. One, vertices, and connectivity. This is actually graph. We can describe a mesh as a graph. Correct. Yeah, this is all about the graph here. Even the knobs. You know what happened behind the scene in the knobs curve? In the knobs curve, I implemented some knobs curve on my work in the company, but what I did is have 2 points, yeah? And then weight, that's it, yeah? And, oh, obviously the connectivity. And then we have an equation, yeah, to drive the multiple point to describe the curve. But only what you need to draw the nice knobs curve is a 2 point and the weight. That's it. Yeah. Also, what I'm saying is we can also convert knobs as a graph data structure.
NJ?
Yep.
I have a quick question. So when you showed polygon modeling, so the way I got it is you break down the modeling into vertices, which will be stored as data structure. And the graph part is the relationship between all those vertices. Like it's stored in a matrix or?
Okay, so if I understand correctly your question, we can do that. We can do multiple ways. So, okay, here is up. Let me open the image again. So, when I say graph, it's a connectivity and between the memory and memory, right? So you can also describe this mesh in a matrix or whatever string, whatever information. But in order to rebuild this mesh out of this matrix or whatever, we need to know the position of the vertices, individual vertices of the dolphin. Correct. And then in order to build the face, I'm trying to use the Rhino API right now. In order to create the Rhino mesh, you need to dump vertex first. And then you need to inject the connectivity. So for example, but this face need to be connected among first vertex, vertex 9 index, and then the vertex in the 100 index. This is memorize the connectivity. So I have an example to rebuild the shape out of OBJ file. OBJ looks like a matrix, but we can rebuild the mesh. And also not only that, but also, as I said, the graph is just remember the connectivity. But inside of this the node, you can save whatever you want. So for example, like, okay, I will draw something because I prepared something for next class, but I can use time. This is a node, right? Node. Mm-hmm. Node number 1, node number 2, 3, let's say 4, yeah, 5. This is, you can see this is vertex, right? Yeah, we can replace with vertices. And then this is connectivity. Yeah. So maybe we need the information, the XYZ, yeah, for vertex 1, 2nd, 3rd, 4th, 5th, right? In order. So this is really important because otherwise we couldn't build the graph here. And also you can build the connectivity. Maybe let's say this is graph, but I'm trying to create the mesh. This is the triangle here, the other triangle here, the other triangle here. So in this case, I can put like simply 1, 2, 3. I'm just put the index here. Okay.
Okay.
Not only that, but also I can create the other matrix. For example, like I don't know, in our network. So for example, how many people visit here? This is one variable. Yeah. Is it already visit by other person or not? This is maybe variable, the Boolean variable I can declare here. Maybe I can declare like the density of a population, what density of a building variable. So these kind of the endless data structure. When I say endless, it's obviously limited, but what I'm saying is you can inject whatever you want, and then you can attach this data to whatever node. So you can expand the data structure. I mean, the graph, pixel, voxel, or this is just like a basic primary concept. On top of it, you can tweak it a lot. Yeah. So let me quickly describe the NNA, the architecture here. So we have the NNA tool here, and then we have a graph system. Let's say you can consider as a graph or tree structure, whatever. And then I have a graph here. Graph has a node, and then it has an edge. And then also we have agent. Yeah. So agent contain origin point. And then also you have like a destination. And then they occupy this graph to compute forward propagation and backward propagation. And all the result is computed. And then I duplicated the node and edge to this agent. Yeah. So what I'm saying is that we have a tree structure, and then also I create the graph, and then also it has a matrix of the node and edge. I mean, there's a lot of freedom. Yeah. So don't stop to like a one single, let's say, twist of source. Yeah. So we basically learn concept, right? On top of the concept, we build something based on your experience and your design target. Yeah. So is it answer to your question?
Yeah. So to conclude, what I got is like the graph, when you say it, it's actually a relationship between all the variables. Is that correct? Like,
yeah, you can consider it like that. Yeah.
Okay.
Mm-hmm. I mean, because the reason I'm hesitating to answer your question is because there's a lot of way. I mean, even the different engineer in our team has a little bit different way of constructing, but the concept is exactly identical. Yeah.
Okay. Thanks.
Thank you. Okay. Let's move. Let me quickly move. Okay. So let me show you my presentation here a little bit. So this is the the pixel graph voxel thing, how we create the apply this kind of concept to the project. This is the geometry, numerical geometry things. I actually have the video here. So this tool is a visualization tool while you manipulating your mesh or surface, visualizing like some inherent information from these knobs, like for the fabrication purpose. It's like a curvature visualization and normal vector and binormal and things like that. I'm also use the graph. Even this one, for example, this is a graph manager. So you can create a connectivity. You can sort based on the distance, or you can give us some, like, let's say, condition. How many neighbors do you have? If you have 5, then visualize. Otherwise, don't visualize. Things like that. This is also talks about creating connectivity things. And the most important thing is that using the graph, we can adopt the spring model. Yeah, it's like a dynamic force. So let me quickly talk about what it does. This is an iterative process. So this is 2 node and edge. We give us fixed number of the length of this edge, correct? Let's say 10, for example. And then whatever force, we keep iterating. And then if the length is bigger than 10, and then they try to gather little bit based on the iteration. And if the length is smaller than our variable, let's say 10, maybe based on your tolerance, and then they try to separate, okay? This is a very basic rule. It's easy to understand, right? So within this kind of relationship, we can make some simulation like this using the spring model. So basically what I'm trying to do is I'm reduce the target string, target length. Based on target length, they're trying to maintain the relationship between the lengths, okay? And not only that, you can use a lot of, let's say here, this is actually one of my research when I was in school. So here, so we have like a swellable material. The material, our assumption is that the swellable material is swell when they expose to sun within certain hours, and then they contract. So I measure the maximum, let's say the swellable size and minimum based on the length. Yeah. So I parameterize the ratio. So as the length is become the bigger, and then the swellable is swell based on the ratio. So we can also do this kind of simulation using the graph relationship. Yeah. Okay, we can jump. We have not enough time. So for application, also so this is the project that I did in the MIT Media Lab. My professor is Kat Larson in the Changing Place Lab. So he and I, we talk about, actually there's a video because I presented this paper to Digital World Futures, but I don't want to spend our time and kill our time because we have limited time. Anyhow, the essence of this one is with our topic is that I parse all the third place data. The third place is basically the place between home and work. Home is the first place, the second place is the working place, the third place is the in-between place, whatever place, coffee shop, ATM, or gym, whatever place, like a park, a library. So I pass all the information from the Google, and then I create some like a graph system, and then I'm trying to parse based on the distance, like 5 minutes walking distance, or 10 minutes, or 15 minutes walkable distance, so that we are able to characterize the particular place with the lens of third place. So this is the result. This is a little video here. Yeah, I'm not going to show you all the video. Just like that. Yeah. So in this case, also you can deploy graph structure to do this. This is the other thing. You know what? Later I will talk about the propagation and back propagation when I talk about the graph things. This is the propagation in a visualization. So you keep calculating because the individual, I mean, think about this is the pixel, like the area, but it has a neighbor like in a 6 direction, but the node has like a particular direction. This is the only difference. So what I'm trying to say is that we can see this image as a graph. So it has a neighbor, right? Yeah, along the 6 axis because this is 2D. So they keep calculating based on the previous pixel, like a previous node, and then they calculate it, and then the result goes to the other node throughout the connectivity. So this is a propagation. And then for the back propagation, for the shortest path, from the designated point, we just find the smallest cost. Yeah, that's it. Back propagation is really faster, but propagation is a little heavy time. Anyhow, so we can expand this one to 3D things. This is one of my thesis. I voxelized the geometry and then train the network. Also, I use again here. And then but my research is how to generate the data to train the network. So I use the multiple way of the like a rasterization of the geometry to train the network. So this is a multiple trial, and then I get this result. And once I got the result, my goal is to how to rebuild the result, the geometry out of the prediction. So this is the video. We can see it because this is really quick video here. Okay. Yeah, so this is the diagram of the workflow. This is how to rasterization. Yeah, I used like 4 different way of rasterization. Anyhow, so I capture all the possible way, and then I'm trying the network, and then this is the how we rebuild the geometry out of this prediction. This is pretty good, right? I actually draw this. Let's say I draw this online, and then this is a prediction image. In the prediction image, they display some of the sense of depth, right? This is a very interesting point to me. So I'm never taught that it has like the armchair, but they give us like some depth here. This is interesting result throughout my research. Anyhow, yeah. Then we can also draw on the screen, and then it spit out the result like this. There's 2 ways. One is to just give us based on the ranking system, we have a multiple like a result, and then which one is the closest one, and then we can spit out as a result. Okay. And the other way around is I'm thinking about like what is the machine creativeness. Yeah. I think a machine creativeness, in my opinion, is an error. How we deal with the error, how we drive the error, and then people can see, oh, maybe some is ugly, some is disgusting, but some is wow. We never thought about it before, right? Then we can consider this as machine intelligence. I mean, this is what I'm trying to say in this paper, but my opinion, yeah, I'm probably wrong, but I don't know. So, yeah, this is the optimization for the parking lot that I did in the Singapore, as I said. Yeah, I will already create a video to describe this one, but yeah, I'm trying to looking at this project as a graph. So here, this is also, we can think about the graph. We have a 2-dimensional pixel, and the individual column could be run like walking around this 2-dimensional pixel. Let's say we can think about this as graph. So there's the agent trying to support the wall efficiently. So the individual column trying to walk through to find the maximum, let's say, the heavy load from the ceiling. This is the ceiling. Yeah, I just put the ground. Yeah, because it's easy to visualize anyhow. So this is also the concept. We can apply the graph concept. Also, the agent-based design. I'm always use the graph because I have a multiple agent, and then I have the other agent, or I have some playground. I control them as a graph. Yeah, graph structure. Okay. And then we have a Json. I don't know how many people you guys have heard the Json data structure, but Json is these days is a, let's say, basic of basic data structure. But when you think about the Json is usually it has like a key and value paired information. So in order to access this value, we need to have this key value, okay? But we can nest them, meaning that we can basically create the graph. Yeah. So let's think about the GeoJSON. GeoJSON is like a conventional, let's say, data structure for the GIS people. So this is the like a syntax, like a promise. We must follow that direction. We need to create the type feature geometry. Yeah, geometry has a point. You can also consider this as a tree. Yeah, point has a multiple, let's say, the array of the coordinates. So we are able to rebuild whatever like a geographical shape out of GeoJSON. So yeah, I'm going to jump this. So again, as I said, in mathematics, the graph is a sort of a main sort of domain. I mean, mathematics, they basically developed the concept of the graph. So there's a multiple types of graph here. This is the direct graph. It has direction, like a one-way tree, let's say. However, we have the other concept, like an undirected graph. So you can do like a round trip, yeah. So the network system in NNA tool, we can support both. But if you use just a default value, this is the undirected graph, meaning that you can travel two directions. And also we have sort of a mixed graph and weighted graph. Weighted graph is an interesting things. So let's say I'm 0 here, right? Please focus. Yeah, this is important. So now I'm going to propagate, right, from 0 to 1. So the cost is 3. So this is becomes 3, right? And then this is 4, right? So the cost already spent 3, right? So I need to sum to the original cost. So the cost is going to be 3, okay? And then also I'm going to do here, number 2, and then 6. I think this is a little bit wrong, but I will draw later. But what I'm saying is that we keep accumulate cost in this direction, and also we can keep accumulate in this direction because simply it has connectivity, right? But in some point, they crash each other, yeah? But when they crash, in terms of the forward propagation, the low cost is always win. It makes sense because we're trying to, the cost function is trying to calculate the network weight based on the distance. Anyhow, I will describe it later. Or if you guys have a question, we have like a daily workshop session. So I'm happy to talk because we have limited time. So I couldn't describe everything. So there are more, yeah. And also, when you construct the graph, the most important thing as a next step is graph traverse. We call it search, graph search algorithm. This is very, very essential for like a one-on-one course for the computer science people. So here, I really like this site. So let's say we have depth first search and breadth first search. This is the way of we travel the network. There's only 2, there are more, but roughly there's 2 ways. So this is the example how the search algorithm is implemented in different sort of algorithm. And also, if you apply as a software engineer job in the United States, you're gonna have a coding exam. So throughout the coding exam, probably you're gonna get like a graph theory. Anyhow, so here's a Dijkstra shortest path algorithm. Let's jump to that session. So this is one of the famous, well-known algorithm for the shortest path. The NNA network is built on top of this algorithm. So I actually tweak a lot, but the baseline is let's say I can say Dijkstra algorithm is the proper way to calculate shortest path. There's a lot of the shortest path or network traverse things. And also, as I said, we have DFS. Yeah. So that first means we keep drill down until they meet the end of the node. Yeah. However, the breadth first search is they visit neighbor first and then neighbor first. It's a bit confused, but don't worry about it. I have an example here. CodePen. So I create some example. So if you are interested in, there's a video I already created in 2 versions, Korean and English. So you guys can take advantage of it. So I just create the graph, let's say class. Don't worry about it. This is the TypeScript. We are going to learn the graph in Python later, maybe next hour. So don't worry about it. Then I create the breadth first search. In this case, we can use the queue concept, which is the one of the concept of the data, like stack concept and queue concept. And then I'm open the console log here. Let's do BFS first. Save. Okay. So now we have a node 0 is a top. Yeah. So what I expect is a 0, 1, 2, because we have breadth first. 3, 4, 5, 6. Okay, let me try to again. 0, 1, this is the step in order. 0, 1, 2, 3, 4, 5, 6. Yeah. 0, 1, 2, 4, 5, 6. Correct. This is a breadth first search. Breadth first search is useful for the shortest path because we need to visit everything. Otherwise, there's no way to calculate the shortest path. And this is the depth first. Again, if you're interested in code is there, link is there. Just access this web and then play with the mesh with the code. Yeah. Here, what I expect is because we have depth first, right? So 0, 1, 3, and then 4, and then 2, 5, 6. Okay, 0, 1, 3, 0, 1, 3, and then 4. Okay, 4, and 2, 5, 6. 2, 5, 6. This is the digit number. Yeah, this is how we traverse the network. So again, let me recap. We have a network. That's it. And then we need to search. We need to traverse the network. There's two particular algorithms: breadth first, depth first. So I implemented the code. So just play with it, please. We already saw this example, and I think I don't need to show you because I already described it, right? You guys already saw it, what's happening behind the scene. So they just trying to maintain the relationship if they're overlapping, and then they're trying to find the better way to represent the topology, right? Because they keep overlapping. But at the same time, they actually print something on the ground, right? Background, the RGB color. So later we can actually extract all the crash or behavior on time. Yeah, this is the beauty of a computation. So that we can track everything. Okay. We have 3 things. Bear with me. Here, this is the other example, just like a pixel, right? So if I zoom in all the way in, I can see 1 pixel. Okay, let me actually screen capture because we have Photoshop here, right? Yeah. Yeah, this is 1 pixel. Yeah, it has a neighbor because it has its connectivity. Ooh, so big, like this, right? You can consider image as a graph, right? This is what I'm trying to say. So in this example, you can see I create this is the convention to generate the D3 WebGL environment, and then I get the image. Yeah. By the way, we have a session because I created a add-on for the Grasshopper. You can do that exactly same functionality in the Grasshopper, so that you can maximize the possibility of using our network system anyhow. So we can discretize the resolution. This is basically what I did is like a tessellate. Yeah, discretize based on this resolution. Yeah, 50 and 50. And blah, 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 blah. And then I pass the color and then apply this color along the z-axis so that we can maintain this kind of landscape here. So here, as you can see, it has a node, and node. Edge is sort of a byproduct by connecting node, that's it. But individual node has not only their connectivity, but also they have maybe slopeness, maybe sunlight if they have the sun direction. If there's some building, we can memorize population density or whatever information, as long as you can detect, as long as you can write, you can resolve, you can save, store all the information on the node, and then we can bring them on the table for your design. I think this is the beauty of computation. Okay. Basically, again, computation designer is to create a system where design can grow, interact, and compute based on our algorithm. The algorithm is our design strategy. Keep in mind. Okay, this is the voxel example. I just extend the 2D along the 3D axis because when I say when I search the voxel, always like this, like Minecraft looks like here. So this is nothing special, as I said. I have only one more loop. This is X loop, Y loop, and Z loop, so that I can create the three-dimensional stuff. Also, this is the OBJ file. OBJ means it has like a vertices and connectivity. Anyhow, we have limited time. I think yeah, I think I'm done. Yeah, so we can have a really quick 5-minute break, and then we can continuously have the session. Any question? It's sort of boring. I can see your frustrated face.
No, I think it was a bit fast at the end.
Yeah.
So I think you'll need some time to digest and like look back and.
Absolutely, yeah.
Yeah, then there will be some questions, I think.
So we have a video, so you can just watch over and over again. Yeah. If you guys have no question, we can have a 5-minute break, then we can come back to continue.
Okay, let's have a 5-minute break and let's get back to the lecture about visualization. It's the third part, right?
Yes, yeah.
Okay.
Thank
See you in 5 minutes, guys. Thank you.
Bye.
Thank you.